In section 6.2 here, we're going to be looking at the applications of right triangles. In particular, we're going to be solving some right triangles and then solving applied problems that involve right triangles or trigonometric functions. First, we're going to look at that solving of right triangles and a quick review of right triangles. So in a right triangle, we know that we have one angle whose measure is equal to 90 degrees. In this case, this is angle C down here in the corner. The measure of this angle is 90 degrees. And then we have two other angles that are acute angles. The names of these angles right now are A and B. So this triangle here is the triangle ABC. So I can make a note of this triangle's name being ABC if I use a triangle. I've just noted the vertices is one way of naming this triangle. And one of the conventions for this particular naming system is noticing that angle A is always across from side little a. So the capital A corresponds with side little a. Similarly, angle B is going to be across from side little b. And angle C is going to be across from side little c. Now, the names A, B, C are intentional in their order. A and B don't matter as much, but C matters just in terms of thinking about the Pythagorean theorem, knowing that A squared plus B squared is going to equal C squared because this is a right triangle. And if the 90-degree angle is called C, the hypotenuse is going to be side little c. So we've got our Pythagorean theorem with this triangle. One more thing to note about this is we can talk about angle A as being this angle right here. We can also refer to that angle as the angle BAC, or in reverse, that same angle CAB. So these are three ways to refer to that exact same angle, angle A right here. And so you'll see it for short notice as angle A, but the angle in the middle of a three-letter pairing right there is the angle that's in question. It's saying, this is a little more formal, it's saying the angle formed by the arcs between B, A, and C is this angle. Okay, so these are just three ways to refer to this angle here. And we're just going to see those coming up in some of the notes, so just wanted to get that out of the way so we were able to notice that as it comes up later on. Now, looking down the next part, so we are going to be able to use Pythagorean's theorem, as mentioned up here, to help us solve the triangles. We're going to solve our triangles, and by solving, that means finding the lengths of all sides and the measures of all angles, given only a few pieces of information to start with. So, in order to make solving the triangle easier, it makes some good sense to develop a system. If we know one acute angle, so either angle A or angle B, we can find the other because we know that angle A plus angle B is equal to 90 degrees. And that's because we know that there's 180 degrees in any triangle. 90 degrees is already taken up by measure C. And so there are 90 degrees left to span angle A and B. So we can subtract to find the other angle. And I mean the other acute angle. Okay. If we know the shortest two sides, that's going to be the Pythagorean theorem to find C. So we're going to know A squared plus B squared equals C squared. We can use Pythagorean. I'm just going to abbreviate Pythagorean theorem right there, Pythagorean, to solve for C. Excuse me. And if we know the hypotenuse in one side, so in the first case, we knew the shortest two sides, so we're saying we knew A and B. If I know the hypotenuse in one side, so A squared plus B squared equals C squared again. In this case, I'm going to know one of the sides and the hypotenuse. Again, I can use the Pythagorean theorem to solve for whatever the missing side is, so B or A or whatever, to solve for the missing side. And then if we know two sides and we want to find an angle, that's where our trig ratios are going to come in. We're going to be able to use trig ratios and arc trig functions or inverse trig functions. So depending on which the two sides you know, if you're looking for angle A, say, and you know the side opposite and hypotenuse, then you would use the sine or the arc sine to find angle A. Or if you knew the adjacent side and the opposite side, you'd use tangent or cotangent to find angle A. So whichever of our trig ratios comes into play, we'll use the trig ratio with the arc trig function to find the angle. So I'm just going to emphasize that piece. We're trying to find an angle. We're going to be using those trig ratios if we have two sides. Okay, so on to, I went too many pages there. There we go. On to the next page. We've got some examples here where we want to solve each of these triangles. There are 4 different examples across this page. Solve the triangle. So I already know a couple of things. So I already know angle C. And I already know side little c. And then I also already know angle B. And I'm going to go ahead and find angle A. So angle A is going to be 90 minus 45, since I know that 45 plus angle A would be equal to 90. So angle A is going to be a measure of 90 degrees minus 45 degrees. So that means angle A is 45 degrees. I already know angle B is 45 degrees and angle C is 90 degrees. So I just went ahead and wrote all 3 of my angles down here now that I know all of my angles. So I was able to use that first strategy because I knew one of my acute angles. I can use the fact that angle A plus angle B is 90, so I subtract angle B over and solve for angle A. All right, so now I know angle A up here. I just figured out that it was also 45 degrees. I also realized because these are 45 degrees, I've got myself a special triangle right here. And I'm going to use that along with one of the trig functions to find my missing side. So I don't know 2 sides. I just know one side and an angle. So I am going to have to use a trig function to find either A or B since I don't know 2 sides. Pythagorean's not going to come into play right now. I'm going to need to use a trig function. So let's work off of angle B, the angle that we were given. And let's say I want to find little b here first. Little b is the side that is opposite to angle B. So if I know the hypotenuse, opposite and hypotenuse are going to be using the sine function or the cosecant function. Both of those use the same too. It's just a matter of which one's on top. So I'm going to start with the sine. And so the sine of 45 degrees, my angle B, would be equal to the opposite, which is side B, over the hypotenuse, which is 10. Now, the sine of 45, that's one of my known angles. So if I look back at my notes from my previous section, we'll remember that the sine of 45 degrees is equal to the square root of 2 over 2. So we'll replace sine of 45 with square root of 2 over 2. That's equal to b over 10. And then to solve for b, we're going to multiply both sides by 10. So that's going to give us, let's see, 2 goes into 10 5 times. That's going to give us a value of 5 times the square root of 2 for b. So I know the measure for side B right here. It's 5 square root of 2. Now I've got a couple of different ways that I can go about finding side A right here. So let me talk through those. One of the ways is because I know this is an isosceles triangle, 45, 45, 90. I know that A and B are the same measure, so I know it's going to be 5 square root of 2. I also, though, could do the sine of this angle and say the sine of this 45 would be equal to A over 10. And that's going to give me the same calculation, and I'm going to solve for A. So I also could use Pythagorean theorem as another way to do this and do a squared plus 5 squared root of 2 squared equals 10 squared and solve for A. But I'm going to go for one of those simpler methods right here. So let me just write down that the sine of 45 degrees, this 45 degrees now, is A over 10. So again, that gives me A equals 5 square root of 2, similarly to what we did here with B. And we knew, of course, that C was 10. So that finishes off our list right here. We know all of the sides and all of the angles. So once we know all of those 6 measures, we've solved our triangle. All right. Let's take a look at the next triangle over here. This triangle is labeled with letters D, E, and F. What I know from this triangle is that angle D is a measure of 30 degrees. I know that angle C, this is E here, different letter. E is a measure of 90 degrees. And then I know the opposite side, which would be little e in this case, is going to be equal to 6. Okay, so first things first, I know that the missing angle, F, is going to be found by taking 90 degrees minus 30 degrees. So that gives me a measure of 60 degrees for F. I already know that D was 30 degrees, and I already know that E was 90 degrees. So I now know all 3 of my angles. And with 30, 60, 90, I know I'm in one of the other special triangle situations. So when I get to my trig function part, I'll look back at my table from the last section or my formula sheets. Now, I know the angle 30 here, and I can find either D or F. Let's go ahead and find D first, our opposite side here first again. So here we have that the sine, since I'm looking at opposite over hypotenuse, the sine of 30 degrees will be equal to opposite, which is D, over hypotenuse, which is 6. The sine of 30 degrees is equal to 1/2. So 1/2 is equal to D over 6. And we'll multiply that 6 over on both sides to get D equals 1/2 of 6, which is 3. Now, I have a couple of different ways to go about finding the value for F, the last side that I'm missing here. I could use the cosine of angle D. I'm probably going to go with that option because I haven't used it yet. I also could use the sine of angle F, the sine of angle F, the sine of 60 degrees. Or I could use the Pythagorean theorem. Now that I know that this side is 3, I could do 3 squared plus f squared equals 6 squared and solve for f that way. Lots of options. No one option is better than the other. I'm just going to go for some variety right here. Let me go for the cosine of 30 degrees. That would be equal to the adjacent, which is f, over the hypotenuse, which is 6. The cosine of 30 degrees is the square root of 3 over 2. No matter which method I use to get my answer, the answer should come out the exact same way every time, no matter which method is used. We'll multiply both sides by 6. And then 2 goes into 6 3 times. So this gives us an f value of 3 times the square root of 3, and we knew our e value was 6, so that gives us all 3 now of our sides. Okay. Let's see, I'm just going to draw a line right here to separate the work, so I can see that was my sine work to find side D. This was my cosine work to find side F. Okay. Lots of options on what I can do once I get down to some of the later details. At the beginning, there was one way to find the angle, because at the beginning I didn't know two of my sides. I just knew one of my angles, so the subtraction was really the first step here, and then lots of options once I get further on into what I can do to find the sides there. All right. The next one says using the standard ABC triangle format. So I'm going to make myself a triangle that has a side of 100 and a hypotenuse. C is in the standard format. In the standard format, C is always the hypotenuse. So we're thinking Pythagorean theorem, a squared, b squared, c squared. So based on the way I drew this is going to be b as the 100, because I drew that side is shorter than this side. This is going to be c as 450. This is going to be a as my unknown for a squared, b squared equals c squared. This has to be my right angle. If this is the side labeled A, this has to be the angle capital A, this has to be the angle capital C, and this has to be the angle capital B. So I've drawn a triangle that's in that standard ABC format. Standard ABC format really just means that C is the hypotenuse, and the two sides are A and B. Doesn't necessarily matter which of the two sides is which. Okay. I don't know one of my two angles in this case, so I'm not able to directly subtract. But knowing two sides, the first thing I can do is actually get my missing side. So we'll go ahead and get that first. So that's Pythagorean theorem. A squared plus b. I was going to write b squared, but let me go ahead and make that 100 squared for b squared equals c squared, 450 squared. These are some big numbers, so I'm going to get a calculator to help me out. I know that 100 squared is going to be that number, 10,000. So if I take 100 squared, it'll have 4 zeros, so it's 10,000. And then I need to do 450 squared. That one I didn't know. That one came out as 202,500. We're going to subtract the 10,000 over. So a squared would be equal to 192,500. And then we'll need to do the square root of that number. I'm just going to copy paste it because it's a little easier for me than retyping the value. And it didn't come out exact. So if it didn't come out exact, I don't want the decimal value. Instead, I want to try to break it down into perfect squares. So I know, for example, that 100 goes in there. So I would have 1925 left. Let me just try that 1925. I know 5 goes into it, so I want to know if 25 does. Yes, it does. Okay, so 100 times 25 would be 2,500. 2,500 is a perfect square. I can check that one. It is the perfect square of 50, which is 100 squared, which is 10, 25 squared, which is 5, 5 times 10 is 50. And then my leftover is 77, so I know that's 7 times 11, and there's no other factors there, so I'm not going to be able to break this down further. So A is going to be equal to plus and minus the square root of the 192,500. We are going to select the positive square root. Still in this section of the chapter, we're not dealing with our position on the XY grid, so everything is positive. That'll change soon. But for right now, we're still positive. And we said we could write this as the square root of 2,500 times the square root of 77. So A is going to simplify as 50 times the square root of 77. Okay. All right, so I've got A, I've got B, which is 100, and I've got C, which is 450. So those are the three sides of this triangle, all exact values. Now we're going to go ahead and look for some of the angles. I know the angle C, of course. That one is our 90-degree angle. I don't know either angle A or angle B. And I want to start with one who uses the ratio of the two numbers that are whole numbers. It's just a little easier to do. So let's say I find angle A. And for angle A, that's the one I'm looking for first right here. B is its adjacent, and C is its hypotenuse. So that would be a cosine function. So I'm going to start with saying that the cosine of A would be equal to the fraction 100 as the adjacent over 450 as the opposite. So the cosine of A is equal to that ratio. So I know that A is going to be equal to the inverse cosine, or the arc cosine. That's one of the notations for the inverse function. The arc cosine of that fraction, 100 over 450. Okay, let me make sure my calculator is in degrees. I think I said it there earlier, so yes, it is. And I'm going to do the arc cosine of 100 over 450. You can reduce that fraction ahead of time if you prefer. It doesn't really matter. I just typed it in its original format. And I got myself about 77.2 degrees. Typically, our angles we just round to the 10th to one decimal place because it's very hard to measure an angle with a physical measurement, a protractor, with more accuracy than one decimal degree. Before I go on to the next part, I also wanted to show if instead of the arc cosine, typing it with the ARC, if you had gone into your functions menu and pressed the inverse trig function button for cosine, inverse cosine of that same fraction, 100 over 450, you do, of course, get the same value. So those two different notations can be used to do the same thing, 77.2 degrees. Now, for angle B, I could use another trig function, and I could do either the cosine with the side A, 50 squared is 77, over the hypotenuse, or the sine with the 100 over 450, or even the tangent with A and B right here. Okay, so I can use any of those things. However, I already know angle A now, so I could also use subtraction. So I'm going to go ahead and use the subtraction to find angle B. I know that there's 90 degrees left over after you take the right angle out. So 90 minus 77.2 degrees gives us an angle B of approximately 12.8 degrees. And then, of course, the angle C, our last angle, we knew was going to be 90 degrees. And so we know all three of our angles here, angle A, B, C, and we know all three sides, so we've got our triangle solved. Okay, we've got another triangle here to solve. This triangle, similarly, is given in a way that I know one angle, so it's similar to the ones above, but that angle is in DMS notation. So I'm going to make sure I give my angle down here in DMS notation also. Okay. So we're going to subtract 90 degrees minus the 28 degrees, 34 minutes. This is going to help us find angle H, missing angle. And when I subtract this, I'm going to use fractions so that I'll hopefully be able to come back out. Let me clear this, put it back in degrees. So I'll hopefully be able to come back out in DMS, which is the degrees, minutes, seconds notation. I'm going to use the calculator to make sure my borrowing happens correctly. I'm going to take 90 minus, parentheses, the quantity. 28 degrees and 34 minutes is 28 degrees plus 34 sixtieths of a degree. There we go. Okay, so I know that my answer for angle H right here has 61 whole degrees and 0.4333 partial degrees. So what I'm going to do next is on that same line, let's just subtract off the 61 to have just the fractional part. And then I closed some parentheses right here. I'm going to multiply that back by 60 to convert those fractional degrees back into minutes. So that's 26 minutes. So working out on an all-in-one line, a little bit messy, but again, just kind of showing what happened there. I can see it's 61 whole degrees. I'm going to subtract out that 61 to find out what the fractional part is, and that entire fractional part, again, times 60 minutes per degree tells me the number of minutes left over. You can also do this by subtracting and borrowing. So you can take your 90 minus 28, which is 62, and then there's a partial left to do. So you've got to subtract 34 60ths from 62. So you're going to borrow off that 1, and you're going to do 61 degrees, and then 1 minus the fraction, 34 over 60. It's just another way of, I don't want it in fraction form. I want it in degree form, so I've got to multiply that by 60. Another way of getting that 61 degrees, 26 minutes. Okay. So we've got our angle H right here. We already know angle G as 28 degrees, 34 minutes. And I already know angle F as 90 degrees, indicated by the box there. So with this work, I have all 3 of the angles. All right, all 3 of the angles. I need all 3 of the sides. Right now I've got 1 pairing. So I know from angle G right here, I know its side opposite. So I can go ahead and find the hypotenuse, or I can go ahead and find the adjacent side, my choice. If I found F, that would be using a sine function or a cosecant function. And if I found H, I'd be using a tangent function. Let's just go ahead and find H first this time. Why not? Because we have not yet used a tangent on the page. So let's just kind of do a demonstration of that. So in G, this would be opposite. This would be adjacent. So the tangent of G, which is 28 degrees, 34 minutes, would be equal to the side opposite, 17.3, divided by the side adjacent, which is side H. Now, I could multiply the H over and then divide off the tangent, but the H is in the bottom, which makes it different from what I did before when I was trying to solve for, say, D or F up here, when I had the number on the bottom and I just needed to multiply the number over. So what if instead of tangent, I use the cotangent? So the cotangent of 28 degrees, 34 minutes, that would be side adjacent, H, over side opposite, 17.3. I'm just going to flip it here because the advantage is then I would just need to multiply the 17.3 over, and I'm going to get the H by itself. Okay. Now, I don't know the cotangent of 28 degrees, 34 minutes, so we're going to do this all in the calculator. Let me make sure I'm in degrees. Yep, in degrees. And we'll take our 17.3 times the cotangent of, and right there inside, I'm going to do the 28 degrees plus the 34 60th, so plus the 34 minutes right there inside my cotangent function. So that entire thing for H is equal to about 31.77. Okay. All right. We need to find F. So again, for F, I have choices. I can use a sine or even a cosine, or I can use the Pythagorean theorem, having now known two of my sides right here. It doesn't matter which of these I go for. Let's say I'm going to go for another trig function, just for fun. So I like to use the angle that I started with just in case. I might have made a mistake, which I don't think I did, but just in case, I'm going to use the printed versions. So with the printed versions here, G to find F, this would be a matter of opposite and hypotenuse. Similarly, with this conversation about tangent, I want this to end up with the F on top. So instead of a sine, which is opposite over hypotenuse, let's go ahead and use a cosecant of 28 degrees, 34 minutes. That's the reciprocal of sine, so that would have the hypotenuse on top and the opposite on bottom. Okay. Advantages, now I just need to multiply the 17.3 over. And then that's going to have F solved for. I can even copy and paste this line and then change from the cotangent function to the cosecant function. And I already have the rest of it typed. So this means that side F is going to equal about 36.18. Now, as far as rounding on here, I did keep two places. Looking back up at the original, it looks like the significant figures here would have been to one place. If I had rounded those to one place, that would have been fine. I've got my H value, my F value, and my G value, which I know was 17.3. So we've got H, F, and G, all three sides, all three angles, so our triangle has been solved. There is no right and wrong way, whether I use the cosecant function, the sine function, the Pythagorean theorem on this last step. It's your choice on which method. I'm just trying to explain the options, and then you're able to choose when you solve these which method you can use. All right, so we're going to get to the next little part here, applications. We begin with this note at the top, powerful point up here. We can solve any right triangle given enough information about it. The hardest part about any triangle-based story problem is going to be deciphering what I know. If I can figure out what the diagram looks like or what I know, I'm able to solve the triangle. So drawing the triangle and knowing what to solve for are the biggest steps right here. So let's take a look at this example. It says, an aerial photographer who photographs farm properties for real estate companies knows that the onboard camera takes the best photographs at a height of 475 feet and a straight line distance of 850 feet. The question then is, what angle should they set his camera in order to take the best photographs? Okay, so this diagram has been partially constructed for us. In this diagram, I know that the height is going to be that 475 feet right here. That's the height of the plane. And then our straight line distance is going to be the hypotenuse. It's going to be a straight line distance if you were able to trace from the farm, wherever part you're trying to take a photograph of, straight to the object from the plane. Okay. Now the angle of the camera is often referred to as the angle of depression right here, this angle theta. And the angle of depression is going to be equal to the angle of elevation. That's important because we want to have the angle inside of the triangle that we're imagining here. A couple of different ways to think about this. You could imagine this triangle instead, where the 450 was here and the angle was up here. And this angle needs to be across from the 450, such as or 475. I just misread the thing. 475 needs to be across from that angle, such as it's across from this angle. So that's one piece of evidence that these two angles must be equal. The other piece is that this angle and this angle are complements. Therefore, this angle must be a complement to the same measure right here. So a couple of different ways to help us visualize how this diagram was set up. Okay, so I'm looking for this angle of theta, which is the angle of depression or elevation, however you want to think about it. And in relation to the values that I know, that's the only piece I need. So I'm going to use the specific trig function that relates opposite and hypotenuse. So that's going to be the sine function. So the sine of that angle is going to equal the opposite divided by the hypotenuse, 475 divided by 850. And then I'm trying to find the angle. So I'm going to have to use the inverse trig function. So the arc sine of 475 over 850. That's the only piece I need to know. So I don't need to find any other parts of this triangle. So let's go ahead and enter arc sine. And you can reduce that fraction first if you prefer, but you don't have to. And this angle comes out at approximately 33.97 degrees. So realistically, they're going to set their camera at an angle of about 34 degrees, as I mentioned. Typically, it's hard to adjust for more than a tenth of a degree. Even the tenth of a degree can be difficult. So I rounded that to two places just because it would round to 34 as a whole number to one place. And so we're going to say it's about 34 degrees. Okay. Just once more to demonstrate the alternate method. If you're using the functions button, we want to do the inverse of sine. It can also be expressed with a -1 in the corner. And that same fraction will, of course, give us the same result for our angle. So you have either notation. You don't need both, but either one of those notations. On paper, you could have written that as sine with a -1. For the inverse sine, your choice. My preference is to write arc sine. You may have your own preference on that. All right, so that's the angle that they should set their camera at. In this case, I don't need to solve the full triangle. I just need to solve the one specific aspect of the triangle that we're looking for. So we're done with that one. All right, so looking down at the next question, no picture. So I'm going to need to set this one up and draw it for myself. A small buoy is anchored 4 kilometers offshore. And it's due west. That's actually going to be important here as well. Due west of a lighthouse. So I'm going to start my diagram right here. I'm going to draw myself a lighthouse. All right, on some pier or something. And the buoy is due west. So north, south, east, west. So the buoy is going to be west. That's the direction of west. So we're going to have just a little buoy here in the water. And that buoy is going to be a distance of 4 kilometers from our lighthouse, right? That's my buoy. Okay, and it was west. So that helps me north, south, east, west demonstrate where that's going to be. 4 kilometers. I need to continue reading here. We've got a fishing boat that is 12 kilometers due south of the buoy. So due south, 12 kilometers. We've got ourselves a boat. Okay, so a little boat down here. And the boat begins to motor towards the lighthouse. So as it's motoring towards the lighthouse, it's going to take the shortest path towards the lighthouse. So that's going to be completing our triangle right here. And in our triangle, it is going to be a right triangle because west and south are perpendicular. So we've got our dimensions set up like this, and we're motoring towards this lighthouse. Okay. So the first biggest step, that is a challenging step, is to draw a diagram based on that description. Then the question here asks me two things, actually. How far is the boat from the lighthouse? That's going to be this distance. And it also asks me, what is its bearing from the lighthouse? So let me talk about bearing when I get there. I need to read some more about bearing. But let's find the distance first. So the distance is going to be from Pythagorean theorem. Since I know two sides, I can find the third side. So 4 squared plus 12 squared equals c squared. That's 16 plus 144 equals c squared. So that is 160. And then if I take the square root of both sides, I'm going to be able to break that down, if I wanted to, into 4 times the square root of 10, but this is a story problem, so we actually don't need the exact value, we need the approximate value. So we can do the square root of 160 or 4 square root of 10, your preference. They both come out as approximately 12.65 kilometers. So that's the distance away from the lighthouse. The boat needs to travel about 12.65 kilometers to get back to the lighthouse. Now, bearing. Okay, so bearing, it's not actually looking for, well, let me try to figure out what the angle is here. Bearing is an angle that's always measured clockwise from north. So if I think about where this boat's north would be, so we have north, south, east, west from the boat. So from north, clockwise from north, would be this angle right here. So I am looking for this angle inside of the triangle in this context to find bearing. So let me call this angle, I'm just going to call it phi. I can pick whatever Greek letter I want, and I'm going to find that angle. Okay. Bearing is measured clockwise from north, so from north down towards the rotation of a clock. I'm going to stop when I hit that arc. That's inside the triangle. And so I can use, I like to use the exact values, even though I could use the hypotenuse now that I know the c value. I'm going to use a tangent because I have not decimal rounded values right here. It gives me just a little more precision. So let's use the tangent of, we call it phi, would be equal to the ratio of opposite, which is 4, over adjacent, which is 12. If I want to solve for phi, we're going to take the inverse tangent or arctangent of that fraction. And you can, of course, reduce that to 1/3 or leave it as 4/12, your choice. So arctangent of 4, oops, I didn't hit the parenthesis there correctly. Arctangent, open parentheses, there we go, of 4/12 comes out at an angle of 18.4 degrees. Now, technically, when navigation measurements are computed, either boats or planes, they typically do measure them in DMS notation. So we're going to go ahead and switch this one to DMS notation for fun, degrees, minutes, seconds. So we subtract off that full 18 degrees. I'm going to multiply the remainder by 60. So I also could say this was about 18 whole degrees and 20, oops, that's a 6, 26. I was looking at that 0 after it. 26.1 minutes, or why not go down to seconds? So 18 degrees, 26 minutes, and subtract off that full 26. multiply by 60 again, 5.8 seconds. So it didn't specifically ask me to do that. It's just something that we're aware of from the previous section, that typically navigational measures, so boats, planes, even navigation in space, use the DMS notation. So giving both, it doesn't hurt to give both. It's okay on this question if you had just given the decimal degree as well, just kind of sharing some extra insight into this one. All right. Okay, so the next question, the Eiffel Tower is about 300 meters high. Using this information and the Google Earth screen capture, what was the elevation angle or angle of elevation of the sun when this photo was taken? Okay, so there is a triangle being made right here between the Eiffel Tower itself, the sun, which is casting its rays down towards the end of the shadow here, and then the shadow itself here as well. It's hard to see from the picture, but this is a right triangle, and the right angle would be here because the Eiffel Tower itself is perpendicular to the ground. So I'm going to redraw this picture more flat since it's kind of angled, peeking down at it. So we've got our Eiffel Tower. This is the ugliest Eiffel Tower I've ever drawn here. But we've got our Eiffel Tower. We've got its shadow, and we've got the angle formed by the sun. Okay, so the Eiffel Tower, we know, is 300 meters high. Now, this tool right here was able to tell me approximately how many miles long the shadow was, but we're going to need to convert that into meters. So I'm just going to use a Google converter real fast. So we're going to convert 0.31 miles into meters. So that's 0.31 miles, or about 498.9 meters. Okay. And then my question on this one is about what is the angle of elevation of the sun. So the angle of elevation, they're asking me this angle right here, compared to the horizon, how high is the sun? So we're looking to find this angle. I'm going to call it theta. All right, so in terms of that theta, I know the opposite and the adjacent. That's going to be a tangent. So I can set this up with the tangent of theta equal to opposite 300 over adjacent 498.9. These are both in meters. They need to have the same unit. And then to find theta, we'll need to use the inverse function. So we're going to do the arctangent of that fraction 300 over 498.9. Arctangent of that fraction 300 over 498.9 gives us an angle of elevation of approximately 31 degrees, 31.0 degrees. Okay. Now, there's just some interesting information at the bottom of the page. It just tells us that if someone knew the angle of the sun, like we just calculated, and the time of the year as well as the latitude in Paris, they could actually calculate the time of day when this photo was taken. This is an example of some forensic photography, and it can be used, there's an interesting article in that link right here, but it can be used to determined that this photo taken during the Crimean War and the photo down here had to be photoshopped or faked because the time of day was the exact same. And so the cannonballs that were put into the road here were put in post imaging. So forensic photography can be used along with calculating these angles of elevations in the sun. So kind of an interesting look at what you can do with trigonometry. Okay. All right, so we're going to continue and look at example 5. Here we've got two people on opposite sides. Oh, no, I misread that. I need to read this carefully. I've done this before. We've got two people on one side of a river. Sometimes there'll be opposite sides. In this question, two people on one side of a river, and they're trying to estimate the width of a river. So let me try to make myself a diagram here. We've got our river here, and we have two people that are on one side of a river, trying to figure out how wide this river is. I need to read some more about their positioning. Okay, so the first person stands directly across from a tall tree that's on the opposite bank of the river. So let me put one person here, and they're directly across from a tree, just a landmark. Okay. So I'm seeing that part of my triangle is going to be the distance or the side that's between these guys. And the tree's on the bank, so it's like right on the edge of the river. The person's right on the edge of the river, so that distance between them should be the width of our river here. And the second person is going to walk 25 yards away along the same riverbank. So the second person walks 25 yards along the same riverbank. So they're going to be up here. And the distance between person 1 and person 2 right here is going to be 25 yards. Okay. And then that second person measures the angle between the first person and the tree as about 65 degrees. So let me draw in the other part of my triangle right here. All right, so when the second person starts to measure the angle, from their perspective, we're looking at it in this orientation, and they're going to measure the angle from person 1 to the tree. So the angle that they're measuring is going to be this angle. This is the angle that they have perspective on, right? They are here, and they're measuring the angle as they see it between the first person and the tree. So that's the arc they're able to observe. Helps me to turn the page. Hopefully that helps you as well to see what we're looking at here. So that's what we're able to see here, right? They measure the angle between the first person and the tree, and that's this angle from their perspective. Okay. Now, the other piece that we do know here is that since this person is directly across from the tree and the riverbed is presumably pretty straight at this point, they've walked in one direction, we do have a 90-degree angle formed in this bottom corner, so we should have a right triangle. Okay. Now this angle that they measured, I forgot to write in the measure, this angle was measured as 65 degrees. Okay. Now, my goal is to figure out how wide is the river. That is the goal, and that's my river width right here. I want to figure out how wide is the river. So let me call this W for the width of the river. If I know this angle is 65 degrees, the width would be the side opposite, And the 25 yards is the side adjacent, so I could use the tangent function. So the tangent of 65 degrees would be equal to the side opposite divided by the side adjacent. It looks like I do want tangent, not cotangent, because in the tangent function, the unknown is on the top. So I'm going to be able to multiply the 25 over to the other side to get rid of the denominator. And then I'm going to know that W is equal to 25 times the tangent of 65. Let's get our calculator, make sure it's still in degrees. Yep, it is. And we need to take 25 times the tangent of 65 degrees. Comes out as a value of approximately 53.6 yards. So the river's about 53.6 yards wide, and then they can decide if they're going to swim it or not based on how far away it is. This, interestingly enough, this kind of process with trigonometry is one of the ways that the early explorers were able to measure distances when they were making their maps. So if you think about lugging trigonometry tables across the country with you to be able to compute the tangent of 65, that's what they would have done. Actually, what they would have done is just made markings and measurements and then done the trig once they got back home. Okay, so we're actually on to our last example here. This one says that cartographers have long made use of trigonometry to estimate heights of mountains rather than trying to climb them. For example, we say that we measured the angle above the horizon for a mountaintop from one position to be 15 degrees. Okay, so we're going to measure the angle above the horizon for a mountaintop from one position to be 15 degrees. Let me draw myself a little diagram to get this started. I've got a mountain, very tall mountain right here, and I want to know how tall that mountain is. So I'm going to measure the angle from my position to the top of that mountain, and I'm going to say it's about 15 degrees. The mountain presumably is going to form a right angle with the ground, right? So it's a right triangle here. Then it's always a good idea to read the whole thing before starting to draw, so I'm not actually doing that, so apologies. I've read this before. But read the whole thing and then go back and highlight and draw. Then we're going to move directly toward it, staying at the same altitude. So we need to be roughly flat. So if there's any hills, we'll go back down to the same altitude. For a distance of half of a mile. So I'm going to move to a position, say here, that is half of a mile away from where I started. So I've moved a distance of 2,640 feet away from my initial position. From there, we stop again and make a similar angular measurement. And this time, we find that the peak is at an angle of 16.5 degrees. Right, so that's going to be my next angle. Okay, use a little bit of algebraic manipulation and some equations to accurately estimate the height of the mountain. So this is my ultimate goal, is to figure out what is the height of this mountain. Okay, so I do know a little. I know two angles, and that those angles were calculated 2,640 feet across. What I don't know is how far away from the mountain I am right here. So let me call this X. And I'm going to make two separate triangles real quick just to see what these look like. So the first triangle is going to have the height of the mountain, the bottom is x, and this angle is the 16.5 degrees. In the other triangle, the height is still h, the angle is 15, and the total across the bottom is x plus the 2,640 feet. Okay, so nothing else is similar about these triangles. These two angles are different, so these two angles are different. They're not the same angle. I don't even need to know what that angle is. But I'm going to be able to set up trig ratios for these two functions, and with two equations and two variables, I should be able to solve that system. Okay, so for this one, let's write this. Let's see. This is going to be tangent. All right, so I want to solve for x. So I'm going to want to have the x on the top. So instead of tangent, which is opposite over hypotenuse, let's go ahead and do cotangent of 16.5 degrees would be equal to, I think I call it hypotenuse, I'm going to call it adjacent. The H is throwing me. H for height, not for hypotenuse. Tangent would be opposite over adjacent. So cotangent is adjacent over opposite. So the cotangent of 16.5 is x over h. I wanted it in that order so I could solve for x because x is the variable that I need to get rid of. So I'm going to multiply the h over. So h times the cotangent of 16.5 degrees is going to be equal to x. Okay. That's what x is equal to in this diagram. In this diagram, h really actually is the thing I'm going to try to solve for because I'm hoping to take this and plug it in for x in that equation, therefore eliminating x, getting an equation that only has h's in it. So let's keep our h on the top here. So I'm going to use the tangent function, not the cotangent. So I've got my opposite over my adjacent. So the tangent of 15 degrees is equal to h over x plus 2,640. I am going to multiply that over to the other side. X plus 2,640 times the tangent of 15 degrees would be equal to h. And then I'm setting this up for a substitution. So I'm going to be able to plug this in for x and then get an equation that's only in terms of h. So we have h cotangent of 16.5 degrees plus, that got plugged in here, plus the 2,640 times the tangent of 15 degrees equals h. I do need to solve for h, and there is an h on both sides. So in order to be able to solve for h, I'm going to need to get them on the same side and factor, which does mean that I'm going to need to get rid of these parentheses right here by distributing the tangent of 15. Let's distribute. So h times the cotangent of 16.5 degrees times the tangent of 15 degrees plus 2640 times the tangent of 15 degrees is equal to h. Now you absolutely could take the cotangent of 16.5 degrees times the tangent of 15 degrees and all of this and make them decimal numbers if that's more comfortable. I'm leaving them exact just because I can, but you can make them decimals if that helps. I'm going to take this entirety and subtract it over. So the 2,640 tan 15 is going to be by itself. It's going to be equal to the h that was already there minus the h times the cotan of 16.5 tan of 15. And then because there is an h in both of these terms, we're going to be able to factor it out. This is a 1h. So when I factor out h, I'll have h times 1 minus the cotan of 16.5 times the tan of 15. Equals the 2,640 times the tan of 15. Okay, quick little division. We can now divide this entire grouping over to the other side, and we'll have solved for h. 2,640 times the tan of 15 divided by 1 minus the cotangent of 16.5 degrees times the tangent of 15 degrees is equal to h. Okay. All right. Again, if it made it easier for you, back up here, just make these into decimal form. You can always have done that. So the cotangent of 16.5, you could have called this 3.4h, right? Times this one. I forgot to do both of them, but you could have made it a decimal. All right, so I'm going to type in the whole thing because I solved for it already. I forgot to hit the division key. There we go. So on the top, 2,640 tan of 15. On the bottom, 1 minus the cotangent of 16.5 times the tangent of 15. And I get a value of 7,413.5 feet tall. So that's the height of the mountain. Just looking for h, which is the height of the mountain. The height of that mountain, 7,413.5 feet. Okay. Imagine doing that as an explorer. You'll make your measurements, go home, do all the trigonometry, and be able to calculate heights of mountains.